Hello, this is extra practice sections 2.2, 2.3, and 2.4 for math 2331 linear algebra. The first question, we want to find the matrix for each linear transformation from R2 to R2. Both of them involve geometry and both of them involve composition. So let's get started with 1a. First, t projects onto y equals 4x. And then t projects onto y equals x. Well, let's say I call this one line 1, and I call this one line 2. Let's write line 1 as a span. Line 1, we can write this as a span of, say, x equals 1 and y equals 4. So the span 1, 4. From this, we can immediately write down the matrix for this projection. It would be 1 over W1 squared plus W2 squared, so 1 plus 16. And then we take W1 squared, we have W2 squared, we have the product, W1 times W2, and the off diagonals. And I'm not going to do much to simplify this. I think I'll leave the 1 over 17 on the outside just to keep the fraction part on the outside of my matrix. And then I have 1, 4, 4, 16. Okay, now let's do the same thing for a projection onto line L2. We could write this as the span of 1, 1, x equals 1, y equals 1. So this matrix, well, it has the similar formula we saw before. It's just a different vector, W1, W2. So we have 1 over W1 squared plus W2 squared. And then we have, well, you see, we have W1 squared, W2 squared, W1 times W2, and W1 times W2. And just, I guess, again, I don't have to, but maybe once again, I will leave the 1 over 2 on the outside. This is a matrix of all 1/2s. In fact, we've seen this before. But even if we hadn't, it didn't take too long to calculate. Well, now let's move on. What we need is the composition, and the order matters here. Definitely, order matters here. So if we read this first, we are projecting onto line 1. That means it must go on this side. And then we are projecting onto line 2. And so the order goes like this. As a comment, these two matrices do not commute. So if you do it in the other order, you will not get the same result. In fact, that would be wrong. But I multiply these two matrices, I think I will pull out the constant in front. Certainly I can. Certainly this is a property of matrix multiplication, and it will just save me from having to worry about fractions too early. Okay, so now, well, we know, for example, we take this row times this matrix, we get the first row of the product. And similarly, we take this row times this matrix, we get the second row of the product, but the two rows are the same. And so I will have the two rows being the same in this product. And they are, let's see, we take 1, 1 dotted with 1, 4, we get 5. Then 1, 1 dotted here, we get 16 plus 4, which is 20. So this is also this row. This is fine as a final answer. Maybe I will go ahead and pull the constant inside just because I can. I get 5 over 34, 5 over 34. And then this other column will be 10 over 17 and 10 over 17. Now, recall that I said these two matrices here, this one and this one, do not commute. And you can think about that geometrically, because what happens second is we're projecting onto this line, y equals x. And you see, looking at our matrix, this column and this column both lie along the line, as they should. Okay. On the other hand, if first you projected here and then you projected here, which would be multiplying in the other order, the columns of that will lie along the line y equals 4x. And that's just not what we see here. So it's important to get the order right when we multiply, when we are composing transformations. So this was 1a. We scale by 4, then rotate, and then reflect. Well, the scaling, I can really take care of at the end. You could write down the scaling matrix to scale by 4, but we're just multiplying by a constant, so I can really do that at any time. So let's do the other two pieces here. For the rotation matrix, well, I give you cosine pi over 3 and sine pi over 3, but my theta is 2 pi over 3. 2 pi over 3 is here with a reference angle of pi over 3. So you notice the cosine is negative and the sine is positive. So let's write this. Cosine 2 pi over 3. The cosine is negative here, so this would be negative a half. And the sine of 2 pi over 3 is square root 3 over 2. We must be able to use reference angles here. Now we can write down this matrix for the first part. Well, it's cosine, sine, and then minus sine and cosine. This is the matrix for rotation by 2 pi over 3 counterclockwise, cosine sine minus sine cosine. Well, what about reflection across the line y equals x? Well, you see here, this is the L2. Maybe I'll write this. This is the L2 from above. And so we've already calculated the projection matrix for this. It's a matrix of all halves. To get the reflection matrix, we take 2 times this matrix minus the identity. And when we do, well, you see what we get. We just get 0, 1, 1, 0. Now we're ready to multiply. We have to pay attention to order here. So rotation happens before reflection. So here is my rotation matrix. And then here's reflection. But I can't forget I have a factor of 4. So let's put a 4 here. In the end, what do I get? Well, I can just multiply this, okay? And then make sure I multiply by constant 4. Okay. So we get square root 3 over 2 times 4. This would be 2 times square root 3. And then here we get negative a half times 4. This is negative 2. Then here we have negative a half times 4. It's another negative 2. And finally, we have negative square root 3 over 2 times 4. This one's negative 2 square root 3. So this will be my final answer here. Next question is just which matrix operations are defined. A is 2 by 3, B is 3 by 3, C is 3 by 2, and D is 2 by 1. Okay, well, we can try to write underneath and then see what makes sense. So C is what, 3 by 2, and A is 2 by 3. Okay, so far I know one answer. It's here, CA. This is defined. In fact, CA is 3 by 3. Let's move on. A is 2 by 3. B is 3 by 3. So far, wonderful. D is 2 by 1. Here we realize there's a problem because here and here, they don't match. And so the product A, B, D, that's not defined. Now let's move on. B, C, D. B is 3 by 3. C is 3 by 2. And D is 2 by 1. Everything looks wonderful here. This is defined. In fact, B, C, D will be 3 by 1. So we want to circle this one. Now, finally, we have matrix times a sum. A is 2 by 3. Inside of the sum, B is 3 by 3. And then C is 3 by 2. Oh, this is the issue. The issue is in the sum part. 3 by 2. Right here is the problem because we cannot add these two matrices. So this is number 2. Number 3, we want to find the inverse of a matrix. Well, what we want to do is we put matrix A over here and we augment with the identity. 3 by 3 identity. Then we perform elementary row operations until we see this identity, okay, something. And then this matrix over here will be the inverse. So let's get started on our row operations. My strategy is to first get zeros underneath this first one. At the same time, we can take -2 row 1, add it to row 2. We take -2 row 1, add it to row 3. We get 0, and then we get -1 plus 2, which is 1. And then we have another 0. And then here we have -2, 1, 0. Don't forget, when you are doing these row operations, not only do you do it to this part, but absolutely do it over here too. That's part of the process. Now, -2 row 1, add it to row 3. We have 0, -3 plus 2, and 3 minus 2. And then we have -2, 0, 1. We see my next leading 1 is in the 2, 2 position. I want to make this -1 underneath that is 0. So let's take row 2, add it to row 3. Row 1 and 2, I am not changing in this step. I get 0, 1, and then we have -4, 1, 1. Now I really only have 2 more steps. I have my leading 1s along the diagonal, which is what I'm looking for. So I only have 2 more steps here. Let's take -row 3, add it to row 1. Row 2, row 3, these are not changing in this step. Well, I get 1, -1, 0, and then I get 1 plus 4. I get 0 minus 1 and 0 minus 1. So you notice I have 1 more step here. This entry needs to become a 0. So let's take row 2, add it to row 1. Row 2, add it to row 1. Over here I have 1, 0, 0, which is beautiful. Then we just add row 2 to row 1 on the right hand side. We get 3, 0, -1. Immediately, A inverse. I see it. It is right here. Copy and paste. And I will add this bracket on this side. This is how we find the inverse of a matrix. So let's underline the inverse here. This was number 3. Now we have 2 more. They're a little shorter than the ones we've been doing so far, and they're both about commuting matrices. The first one, we're given these 2 by 2 matrices, A and B. Find the constant K such that A and B commute. So what we need to do in this problem is multiply AB and BA and then set them equal. We should be able to find the constant K. So A is the matrix 5, -3, 0, 2. B is the matrix K, 5, 0, 4. So I want to multiply in both orders. You see, we get 5K. Zero. We have -3K plus 10. -3K plus 10. Let me scoot this over. And then the final entry, we have 8. Well, let's multiply the other side. We have 5K plus 0. So this is 5K. So far, just equating the 1 entries, we have no restriction on K. But then we have this, which is 0. Here we have 25 minus 12, 13. And finally, we have 8. Well, you see, looking at these, that those all match. And so we just need to set the row 2, column 1 entries to be equal and solve for K. We get minus 3K plus 10. This is 13. Now subtract 10 from both sides. We have K as -1. This is my answer here. This is number 4. Now here's the very last one on this extra practice worksheet. Suppose A and B are n by n matrices that commute. Do A squared and B commute? This is fantastic question because we have to think, but the answer is yes. Why would this be? Well, I need to justify that A squared B equals B A squared. That's what it means to commute. But you note that A and B commute. So I can write A squared B as A times AB. Well, if you look here, I can interchange the order because AB equals BA. So this is A, BA. Well, I can do it again because here, AB equals BA. So this is BA, A. And this is B, A squared. Okay, so I've used that matrices A and B commute to say that AB equals BA. And then I did it again on the next line. Maybe I'll underline that part. Here, I used AB equals BA. So I used the commuting aspect twice, but the answer is yes. This is our third extra practice worksheet. Thank you all so much, students.